and welcome to the Forestry Adaptation Community of Practice webinar today. For those of you who don't know me, my name is Annette Morand, and I am facilitator of the online adaptation communities of practice, which are run by us here at PR, which is the Ontario Centre for Climate Impacts and Adaptation Resources, and we're located at Laurentian University in Sudbury, Ontario. So the way the webinar will run is as follows. So after this very short introduction, we're going to have the main presentation, which will go for about 40 to 45 minutes. And then at the end of the webinar, we're going to have some time left for any questions that you might have for Caren. So as we go through the webinar, please feel free to post your questions in the chat box, and we can address them during the Q&A session at the end of the webinar. And before we get going, I just have a few housekeeping items to go over. So first, for those of you who dialed into the conference call line, your lines have been automatically muted. And the reason for this is just to avoid any audio distractions or feedback during the webinar. So to ask a question during the Q&A session, all you're going to have to do is dial *6, and that will unmute your line. But please do keep your lines muted during the presentation. Also, if you have any technical difficulties during the webinar, you can click on my name and the attendee list and send me a private message, and I can try to help you as best as I can. I also want to mention that we are recording the webinar today, and I'll be sending out a copy of the recording to all those who have pre-registered with me, and we'll also be posting it to the Community of Practice website. And finally, I know that we have some people on the line who may not be familiar with what the Forestry Adaptation Community of Practice is. So I wanted to just take this opportunity to quickly mention that it's an interactive online community, and it's dedicated to those who are working in forestry or simply interested in forestry and climate change adaptation in Canada. It includes features such as an online resource library, news articles, discussion forums, and more. And it's free to join, so if there's anyone on the line today who's interested in learning more about the FACoP, please click on the link in the chat box for more information and to register. So with that being said, we're very excited to have Caren Dymond on the line with us today to talk about how climate change might affect forest growth and what we can do about it. And just so you know a little bit more about your presenter, Caren is a forest carbon and climate change researcher with the Government of British Columbia and has a background in carbon modeling, natural disturbances, ecological modeling, and geomatics. She holds a master and bachelor degree in ecology from the University of Calgary and is a professional agrologist. After finishing her master's, Caren started her career in landscape ecology lab at the University of Wisconsin-Madison and then worked for the Canadian Forest Service on various projects for 8 years. Since joining the Government of British Columbia in 2008, Caren's been working on 2 main research programs, including accounting and forecasting the impact of different management choices in climate change on the ecological goods and services of forests, and understanding the carbon footprint and sustainability of forest products. And using this knowledge, she leads and collaborates on developing evidence-based policy for British Columbia. So on behalf of everyone joining us, I'd like to extend a very warm welcome to you, Caren, for taking the time to present this webinar today. We really appreciate it. So without further ado, I will now turn things over to you.
Thanks, Annette. It's great to have this community. And thanks everybody who's on the line. I really appreciate having an audience, even if I can't see you. And just to give you a heads up, there will be a quiz halfway through the talk. I'd like to acknowledge a number of different collaborators and people that we get support and advice from. This is certainly not a one-woman show. And we get funding support from our internal natural resource science program. So I'd just like to talk a little bit about how I came to be talking to you today about climate change and forest management. So I work in a lab in the University of Wisconsin-Madison where I learned about an ecosystem model called Land2 and was working on some route sensing products in that lab. And then I moved to the Canadian Forest Service in Edmonton, and I was working on a forest management international development project, but down the hall there was people working on climate change impacts on forest fires and the increasing annual area burn that they were forecasting, quite alarming for the boreal forest of Canada. I then escaped from Edmonton and moved to Victoria, still with the CFS, and I was working on remote sensing of mountain pine beetles. So this image is just the Google Earth image from 2017 around Prince George. But if you look at the 2000 image, it's all pretty much dark green, whereas here we have a lot of light green and a lot of light green and a lot of rectangles where there's been harvesting occurring in the meantime. And of course, the mountain pine beetle outbreak in BC is in part a climate change impact. Then I moved to the carbon accounting team in CFS Victoria, and we looked at the impact of the mountain pine beetle and wildfires on the carbon fluxes of British Columbia and Canada, and found that there was these natural disturbances had a high probability of turning the forest from being a sink to carbon into a source of carbon, so potentially creating a positive feedback mechanism to climate change. The political cartoon on the left was in the Edmonton Journal after one of our papers came out, and I thought it was kind of funny, but also, you don't go into science expecting to be in the editorial cartoon piece. Then I moved to British Columbia as a research scientist, and I started trying to work more actively on the forest management, the what can we do about it side of the climate change question. This graph is from a study where we said, well, what can we learn from the mountain pine beetle outbreak? So we started in 1980, ran models of different management options through out to 2060, and we found that strategies that increased tree species diversity before the beetle hit meant we would have higher harvest rates and higher resilience post-beetle. But one of the criticisms of those studies was that they were historical retrospective. So we don't have that inventory anymore in British Columbia. So people wanted to know, what can we do going forward? So that brings us to today. So there's two parts of this talk. The first part is focusing on study area in Northwestern British Columbia, where we look at climate change impacts. And then the second part is on the adaptive planting. So this scope kind of focuses on my research program. This is one of my research programs on climate change impacts and how can we manage our forests for the future. And we're focusing in this talk on timber supply, carbon, and species composition. But we have another project underway where we're also looking at water and hydrology. So there's a quote here in the box: all models are wrong, some are useful. And I like to add in, when I'm showing model outputs from that project the future, that I'm not a wizard, so I can't actually predict the future. These are models, and we hope that they are useful for forest managers and decision makers going forward. Okay, so a lot of the metrics I'm going to show are forest carbon metrics, but I will try to relate them back to forest management. So there's a couple slides here on background of forest carbon, because I don't know exactly where everyone is coming from. And why do we care? So climate change is really forcing us to understand the carbon that's stored in the forest, opportunities for sinks, opportunities to reduce emissions to that atmosphere to help reduce the likelihood of the worst climate change impacts. We're also getting questions from stakeholders, and I'm sure many of you are as well, as to what we're doing in our management of forests in terms of adaptation and climate change mitigation. So these questions are coming to various people at various levels. There's also new opportunities for business. So we export approximately 2 million tons of wood pellets from British Columbia to Europe. because of the demand for renewable energy because of climate change concerns. So this little diagram here is just to remind everybody about forest carbon cycle. So there's a pool or a reservoir of carbon dioxide in the atmosphere. As trees grow, they take up that carbon and store it as cellulose and lignin in the wood, and it can be stored there for years, decades, centuries. But also in the forest, there is decay happening. So as leaves fall, branches fall, trees die, they rot, and some of that carbon is emitted to the atmosphere. But again, there's a large carbon pool in the coarse woody debris and in the soil that can be a large pool or a small pool depending on various disturbance factors. Now, of course, when there's a fire, lots of carbon's emitted. When you have a forest that is disturbed, such as by insect or pathogen, then we call these two conditions where the forest is the net source of emissions to the atmosphere because the growth rate isn't enough to overcome the decay rate. Whereas in this healthy forest, it's probably a net sink of carbon from the atmosphere as the trees grow. Now, of course, when we harvest, we remove carbon in the form of logs from the ecosystem. Some of that carbon is emitted during manufacturing or construction or for bioenergy, and some of it is stored for years or centuries. And then when we go in and plant, we are trying to speed up the conversion of that stand back to being a net sink by accelerating the tree growth to overcoming the decay. So the first study I'm going to talk about is the contrasting climate change effects that we found in this study area in Northwestern British Columbia. So this area is just near Smithers, just west of Smithers, called the Copper Pine Creek Valley. So this area here on the map is actually the town of Smithers. And then the valley runs east-west here up to tree line. So this oval in the study area map is Hudson Bay Mountain. That's in the photograph. And the photograph is just to give you a sense that the topography, fairly rugged topography, that means we have quite a difference of climate within a relatively small study area. I'm going to focus on two regions. I'm going to try to call them regions, modeling regions, not ecoregions, but if I slip up and say ecoregions, I don't mean like the National Ecoregions of Canada or anything like that, just what we use in the model to define areas of relatively consistent climate and climate envelopes and the tree productivity associated with those regions. So the purple area is cold, it's the spruce fir forest, and then this green area here is region 7. It's the warmest in the study area, and it's dominated currently by pine, aspen, and spruce. So region 3 here is a mean annual temperature of 1.4 degrees and over a meter of annual precipitation on average, whereas the warmest ecoregion is temperature of 3 degrees and less than half the amount of precipitation. So quite different growing conditions. The methods, I'm not going to spend a whole lot of time on this because I could go on for a long time. But just to sort of focus on the key part of the methods is that we simulated the model forest ecosystem from 2012 to 2050. So relatively short in terms of forest planning or tree lifespan. And we took an ensemble approach. So if we're looking at future climate conditions, there's quite a range of possible climate conditions depending on which model you use and which emissions, how much emissions you assume people are going to produce. So we took an ensemble or aggregation approach to those 5 different possible futures. So the scenarios that we modeled are no climate change. So the productivity in the future would be like the past. average productivity from those 5 possible futures, and then a high and a low. Just to basically try to understand the bounding box of possible futures in this landscape. The model we use is called Landis-2. It's a spatially dynamic forest landscape simulation model. And during this project, we also developed a new extension to Landis-2 that can track carbon stocks and fluxes over time. So we included in our simulation harvest and planting and fire. Because this was the first time we'd used this model in this study area, we spent a fair amount of time trying to build up our own confidence in the credibility of the model output. Part of that involved back calculating from carbon the merchantable volume and creating these kind of growth curves that you see in the graph, and comparing those with the Ministry of Forest growth and yield models, and having local experts review them and provide feedback. Because we're not using the model here to understand the ecosystem, we're trying to use it to understand more about climate change and forest management. And then we compared the carbon stocks and fluxes with published values for similar forms. So here's some results. The top left graph is region 3, so this is the colder one, spruce fir forest. The gray line is no climate change. The black line is average productivity, and then there's the blue and red are the low and high productivity scenarios. The indicator here is net primary productivity, and that is roughly equivalent to annual increment or growth rate. So you can see for this region, there is generally a projection of or expectation of increasing productivity over the 40, 50 years of the study under climate change. Region 7, though, is a bit different. So here we have the high productivity scenario under climate change is roughly equivalent to no climate change scenario. So the best this area is going to do is hold its own. All the risk here is on the downside from climate change. So what we think is happening here is that region 3 is a colder and wetter environment. So the tree growth rates currently are constrained by temperature, not water. And so when the temperature increases, they can take advantage of that. Trees can take advantage of that and grow faster. Region 7, however, is the productivity currently is limited by water. So when the temperature goes up, unless it gets hotter and wetter, then the productivity will go down because it's already drought limited. So these indicators are above ground biomass. So this is basically like the growing stock. How much biomass is there in the living trees? So for region 3, it really follows similar to the productivity, where the projections are increasing biomass over the 50 years of the study. Region 7, here where it's not, the biomass isn't even holding its own under the high productivity scenario. All 3 of the climate change scenarios have lower biomass. In terms of carbon balance, if we look at the net biome productivity, here we have on the left is, again, region 3, follows from the net primary productivity graph, where we have the forest moving from being small sources to being small sinks due to that changing climate and associated productivity. Region 7, the no climate change scenario in gray kind of bounces around the 0 line, but is a small source of emissions to the atmosphere, whereas under all the climate change scenarios, it generally tends to be a larger source to the atmosphere. So again, this is coming back to that feedback, positive feedback mechanism or risk that we're facing in the forest. So here is a map of the carbon balance. This is the same indicator, just on a 1 hectare resolution. So the light green that you see dominating the starting conditions is a small source of carbon to the atmosphere. In 2050, under the high productivity scenario, you have more of this blue, which indicates a small sink of carbon across large parts of the landscape. But if we look on this eastern edge, starting conditions are blue, small sinks, but at the end there's a lot more of this orange, which is larger sources. If we add up the whole landscape and we look at the growing stock or above ground biomass, we see that climate change and no climate change scenarios are very similar, and there's a wide range of uncertainty around those two lines. So some of the areas increase in biomass, other parts are decreasing, so when you add it all up, it kind of gets muddled together. I had a sneak peek at the registration list, so I threw in this graph with the net sector productivity. So this is the carbon balance that takes into account storage in harvested wood products. So it's the net primary productivity minus the heterotrophic respiration, disturbance emissions, and emissions from harvested wood products. So here we see the no climate change scenario and the average productivity scenario largely overlapping and being small carbon sinks, but there is, again, a wide range of possible futures in terms of the carbon balance for the whole landscape. For harvest, we didn't see climate change signal coming through in the harvest volume, annual harvest volume. We think this is largely because of the landscape. So most of the trees here are over 100 years old, or stands at least are over 100 years old. So the volume that we're harvesting is largely already existing in the valley. Remember, this only goes out to 2050. So if we look further out into the future, where we're harvesting second growth, we would expect to have the variability in productivity have a larger impact. So for this study area, given these results, we have some mitigation and adaptation options that jump out. Adding warmer climate species to Region 7, such as Douglas fir, seems like something worth exploring for sure. And somebody suggested that if those productivity rates are being realized in the colder East Coast regions, then they might be more economical to harvest. Okay, so in summary, if we're looking at the average productivity scenarios, lower productivities improved as carbon sinks, but it wasn't enough to counter the poor outcome for carbon sinks and increased sources in the areas of the valley that are currently higher productivity. And what we think is the species are moving away or towards our optimum conditions. So in the colder regions, they are, as the climate warms, they are moving. The conditions around the species are moving closer towards the species' optimum conditions, so they increase productivity. Whereas as the climate warms in the higher productivity areas in Region 7, then the weather growing conditions are moving away from their optimum. Okay, so we have this large natural risk. How do we manage it? And that's the next phase, looking at management options. This is published. We published this paper in 2016, and it is open access. Okay, now for the quiz. Annette? There we go. So given these different effects of climate change, what forest management options would you like assessed in my research program? So there's 4 different options there. And while you're voting, I will just ask Annette if there's any questions.
Yes, I mean, we do have a little bit of time here for questions as people answer. but I don't see that we have any in the chat box. So I guess I have my own question here. So Caren, you only presented 2 regions. So can you tell me what the climate change effects were on the other regions that you didn't present?
Yeah, absolutely. So there were 4 regions that are predominantly England spruce, subalpine fir, and they all tended to have increasing productivity. There's the other 2 regions. One of them was similar to Region 7, is that it tended to have the risk is all on the downside. Best case scenario is that productivity in the future is like it's been in the past. And then in sort of a mid-slope, mid-elevation, it was very muddled. So there was no clear trend in one direction or the other.
Perfect. And we do have a question here from Martin Watts. How do the latest changes in TAS and TIPSY yields affect the results of your study?
They don't, so we didn't use TAS or TIPSY. We just use it to help with the calibration, to make sure that the Landis output was reasonable. Okay, well, let's go on. Looks like different planting regimes is overwhelming success of this poll, so that's good, because that's the first thing that we did. Okay, so part 2, testing novel planting regimes. So when we think about adaptation of forest management, there's a variety of different options that are suggested. And we don't know if those might have positive or negative consequences or trade-offs for different ecological goods and services that we expect from our forest. So something that might be great for timber supply might not be great for carbon or wildlife, vice versa. And then if we look specifically at the options around planting alternative tree species, there isn't really a lot of information on the effects on carbon pools or carbon sinks and emissions. So the aim of this particular study was to stimulate the impacts of different plantings and regimes and climate change scenarios on carbon pools, sinks and sources, tree species diversity, and harvest levels. So I want to give a little bit of background to answer the question that we identified on the previous conclusion slide a couple slides ago, and that is, how can we manage natural risks? And there's more than one answer to this question, but the one we focused on comes from ecological resilience theory. So our ministry published a technical report in 2009 that recommended ecological resilience and complexity as a theoretical framework for helping manage British Columbia's forests going forward. And resilience, you can see the definition here, but it's basically you have a spruce fir forest, it's burned in a wildfire, it naturally comes back as a spruce fir forest. That is a resilient ecosystem. If it comes back as moose habitat, willow, brush, that is a failure of resilience. Now, one aspect, and only one aspect of resilience, can potentially come from species diversity. So in biology, we have this insurance hypothesis, which states that greater species diversity reduces the impacts of disturbances. So it buffers productivity, but also that it increases productivity. And this is, similar to the advice an investment broker will give you about your RSP investments. Don't put all your eggs in one basket. Have a range of different investments because you don't know what different sectors of the market will bring. In the photos here, we have 2 different stands hit by mountain pine beetle. We want more of the one on the right and less of the one on the left. So same study region. The one thing I want to mention here is that it's It's on the east side of the coast mountains, so it's where the coast and interior climates kind of meet, the transition zone. So depending on which climate model you use, it might say the climate is going to be more like the coast, so wetter and more moderated temperatures, or more like continents or interior BC, which is drier and more extreme temperatures. Again, we're using the same modeling platform. We did add pine beetle and ran out to, we used a new inventory because the inventory had been updated, and ran out for 100 years to 2114 to try to capture more the dynamics that would come from planting different species. So this is kind of an ugly table for a talk, but we'll see how we do. These are the different planting regimes that we tested. So there's 1, 2, 3, 4, 5, 6 here. So there are stocking standards in British Columbia that have already had some climate change adaptation introduced. And then to those stocking standards, we added Douglas fir, lodgepole pine, ponderosa pine, or western larch. And then the 6th one was a diversification regime, trying to test this insurance hypothesis and how well it might work in terms of the resilience in this study area. So the planting regime varied depending on where in the study area you were. So as I mentioned, the regions represent the productivity areas of climate envelope. So 3 and 4, the stocking standards is spruce and fir, and then from our productivity model, the Douglas fir, we weren't expecting it to do very well, but we did test adding lodgepole pine. The region 6 is fir and hemlock. The diversification regime added Douglas fir, lodgepole pine, western larch, and western red cedar, because it can potentially grow in that climate envelope. Okay, I'm not going to spend any more time on this, but we have it all written up if you're interested in the gory details. So in terms of climate change scenarios, instead of using an aggregate approach with the average, high, and low, we did the modeling splitting out the possible future climates. So again, we have a baseline with no climate change. Productivity is future, depends on the past. Hotter, wetter, warmer, and hotter and drier scenarios. So this is the mean annual temperature, hotter and drier and hotter and wetter. Mean annual temperature looks like it's going to increase by 6.5, 7 degrees. The warmer is a little bit lower, 5 degrees. The warmer versus hotter is just my descriptions. Give me something to talk about other than using the actual, difficult to pronounce models and runs here. Annual precipitation. The warmer is quite similar to, doesn't change as much anyways as the other two scenarios. And the difference between the hotter and wetter and hotter and drier is 350 millimeters a year, which is a lot if you're a tree. Okay, so let's first look at tree species diversity. So this is the run under stocking standards, year 0, which is 2014, and year 100. So there's a lot of this olive green color, which is the alpine fir, gold color, which is lodgepole pine, and then on the eastern edge is the brown trembling aspen. Under the stocking standards, we see a lot more orange, which is interior spruce that's coming in through the planting following harvest. And then in the southeast corner, we see western larch, which isn't native to this immediate area, but under the climate change adaptation stocking standards, it's allowed to be planted, and it's doing well enough to dominate these stands. So this map on the left is the same as the one we just looked at, year 100 stocking standards. The one on the right is under the diversification regime. So here you see the dark blue western larch in the southeast corner again, but also occurring in the northeast corner and up the valley. Now in the valley bottom, you see this teal. That's Douglas fir that's being planted in these model simulations and is doing well enough to be the leading species. If we look at species diversity in terms of an index, Shannon Diversity Index, under the baseline climate, actually under all the climate conditions, the diversification regime is this dotted one, and it's doing much better than all the other ones, including the stocking standard, which is this black line. Not a huge surprise, given that that's kind of the point of that planting regime. Okay, so if we look at productivity and biomass and carbon balance, the above ground biomass, remember that's kind of like growing stock. If it gets hotter and wetter, expected to increase. If it's warmer, not also increase, but if it's hotter and drier, it's projected to sort of flatline. Primary productivity, net primary productivity, which is kind of like the growth rate, increase if it's hotter and wetter, decrease if it's hotter and drier. Carbon balance, the hotter and wetter or baseline climates sort of bounce around 0. Warmer or hotter and drier are carbon sources to the atmosphere. So basically what we're saying is we can't really predict the future, at least in this study area. But that doesn't mean we can't do anything about it. So here are the planting regime's effects on biomass under the 4 different climate scenarios. And you can see this blue line here is the diversification regime. And it has, in all the 4 different graphs here, it has higher biomass over time than the other planting regime. The dashed purple line, here, maybe down here it's a bit better, is the stocking standard. And it's either within the crowd of the other planting regimes or on the lower end of the group of different planting regimes. If we looked at the effect on harvest, now what we see popping up to the top here is this black dashed line. That is the adding lodgepole pine regime. And part of what's driving this higher harvest volume is because lodgepole pine can be harvested at age 50, and the other species can't be harvested until they're 80 years old. So that's driving part of this result. The diversification regime is lower than sort of the crowd in the middle. And I'm not sure exactly what's going on there, given that it has more biomass available. There might be something funny going on with the modeling of harvest, but nonetheless, this is the results we have right now. If we look at carbon balance, these graphs are kind of hard to read, so I've just focused on 2 climate scenarios, the hotter and wetter and hotter and drier. The carbon balance for the diversification or no management regimes are here, and they are carbon neutral or small carbon sinks. I shouldn't say carbon neutral, sorry. Around 0 or small carbon sinks, whereas the stocking standard under the hotter and wetter is a carbon source. Under hotter and drier, you can see the whole graph tends to go down instead of up. The diversification regime, however, is the smallest source of emissions, and the stocking standard is overlapping with the lodgepole pine and the Douglas fir, adding Douglas fir regimes here, the larger end of the carbon balance, carbon sources rather. So our conclusions are that the future productivity depends largely on which climate scenario occurs, and we don't, it's not really something that we have much control over. We've also found that management can make a difference, that the stocking standards are not optimal for the indicators that we looked at, but that we found the diversification planting regime had higher resilience for carbon sinks, carbon storage, and species diversity in terms of ecosystem services, but wasn't great in terms of harvest. Expanding the planting of lodgepole pine appears to be a good alternative, but there are risks associated with it that weren't in the model. So we did have mountain pine beetle in the model, but this is a high snowfall area, and it's currently not planted in those regions because of snow press damage to seedlings. There's also been quite a bit of documented rust problems within this area of British Columbia on pine specifically. So it wouldn't be high on our list of recommendations. So we're currently working on an economic analysis of these different planting scenarios to see how that would play out, and looking at doing some field work assessing different harvest systems effects on forest carbon stocks using the Date Creek experimental forest. So again, thanks for attending. As I mentioned, the first part of the study is published. The second part is soon to be published in Ecosphere. So back to you, Annette.
Great, thanks, Caren. So we now have about 15 to 20 minutes left for questions. Again, if you'd like to use the chat box, please feel free to go ahead and type out your question. And if you're on the conference call line with us and you'd prefer to ask a question over the phone, just hit *6 and that will unmute your line. So I see that a few people are writing. Give everybody a few seconds here. In the meantime, Caren, I have a question for you. Would you consider planting non-native species in your modeling?
Well, the Office of the Chief Forester in British Columbia has made it clear, at least to date, that we're not looking at species from, Washington, Oregon that don't already occur in British Columbia. I mean, we have quite a wide range of climates already. The one we moved the furthest in our modeling was ponderosa pine. It does grow in the town of Smithers in people's gardens, so we thought, well, we should try it out. It didn't do very well, so it's probably not particularly viable that far north, but and I don't know if that would be acceptable policy anyways. But yeah, so it's more about facilitated migration in British Columbia is kind of where we're focusing on within our ministry and research programs, rather than assisted migration, where you're really bringing in species from quite a bit further away.
Awesome, thanks. Great. So we do have a question here from Joanne Ho. Actually, a two-part question. So does your study include underground biomass? And will your economic analysis include market price sensitivities? So for example, lodgepole pine historically has a very low market demand and is typically left unharvested.
Yes, this study includes underground biomass, coarse woody debris, forest floor, and soil carbon. The economic analysis will include market prices. It's not typically left unharvested in British Columbia. Well, maybe historically pre-beetle, but because it is a lower value log than spruce and Douglas fir. So yes, some of those sorts of things will be taken into account.
Perfect, thanks. Okay, another question from Eric McNaughton. Is there a risk of new pest species affecting forests in future climate scenarios?
So we haven't included new pest species in our analysis to date, but certainly it is a risk because pests move faster than trees do. And then we have, of course, global trade helping bring in invasive alien species. So those are risks. Unfortunately, there's very little quantitative modeling of pests available. There are a number of entomologists working on it, but they're just not there yet for me to take them what they've done and build it into our modeling. It's just kind of a risk that we can identify that diversification would help reduce.
Perfect. Thank you.
Mixed-wood stands versus... Oh, sorry, go ahead.
Oh, no, you can go ahead.
Okay, any thoughts on mixed-wood stands versus primary softwood stands? So from a carbon perspective, carbon doesn't care if it's aspen or spruce. So there is, and then of course fire can have different behaviors in deciduous stands than in coniferous stands. So there may be reasons to have more mixed wood stands. And there is mixed field data results in terms of productivity of especially pine, but other coniferous species mixed with deciduous species. Some silviculturists tell me monocultures are the best thing since sliced bread, and others tell me, well, no, we need these mixed species actually do better, although they may not be as economically valuable from a harvesting perspective. So there's lots of trade-offs in our natural resource management that I'm sure lots of you are familiar with.
Perfect. Great. I see multiple people are writing. This will give us a chance to go to the conference call line. So if anybody has a question over the telephone, just hit *6 and that will unmute the line. If nobody has questions on the phone, we'll just give everybody a few more minutes here to type out their questions. Okay, so a few came in here. So Harshan's question. So the paper on carbon sequestration talks about the introduction of a new carbon indicator and net sector productivity. Is there anything you can share relevant to that?
Yeah, when I went and looked in literature, I couldn't find something that, a term that would describe the balance, the carbon balance of the ecosystem that took into account the fact that some of the carbon removed due to logging is stored for, years or centuries. And so we came up with this net sector productivity. So there's net primary productivity, net ecosystem productivity, net bioproductivity. And so we thought it made sense to have a net sector productivity that acknowledged some of that carbon is stored, even though it's removed from the ecosystem, in order to have a metric that allows us to consider mitigation options, climate change mitigation options, and climate change adaptation options that reflect that whole life cycle.
Perfect. All right. So the next question here is from Frank. So does the various soil types allow for such a diversification? So can tree species be moved from one soil type to another?
Right. So that's a good question, and of course it's going to depend on where you are and what you're considering planting. I took them out of this presentation due to time, but there has been some off-site planting trials, both formal experiments and more informal trials across British Columbia, that including in this part of BC, that have shown like one of the species we propose planting is Douglas fir, and there's a stand of 18-year-old Douglas fir that somebody planted 20 years ago that's doing great on that same type of growing condition as in our study area. So there is some experimental evidence, empirical evidence of some of the things that we're trying to propose in our modeling, but absolutely that has to be considered. Some of the models, show, oh, well, trees are just going to move uphill, but and tree line is going to move uphill, but often the soils uphill don't support trees, so that's certainly something to take into account.
Great, thanks, Caren. Okay, the next question is from Paul. So the Shannon Diversity Index takes into account not only the number of species found in a given area, but also the abundance of the species. So does that model, is it able to predict the number of species in abundance in the future?
Right, so the Landis 2 model can do multiple species and multiple age cohorts on a given grid cell, so it's raster based. Here we modeled it using 1 hectare grid cells. And so what we used as a measure of abundance was for the leading species baths, for example, was which one had the most biomass in the grid cell, which species had the most biomass, and that was what we called leading species. For the Shannon Diversity Index, we've considered the biomass of all the species present within each grid cell to calculate the Shannon Diversity Index.
Great. Okay. So Bill Richards' question here. So you've sort of implied that future climate scenarios, hot, wet, and hot, dry, are equally probable. Is this really true for northern BC? I think the most model scenarios for Canada imply greater precipitation.
Well, I don't really know which one is more likely. They are, it comes back to that I'm not a wizard kind of thing. So maybe they're not equally probable. I don't know, but there's such a range out there from different global climate models that it's really hard to say which one is more or less probable from my perspective, at least. The precipitation is certainly way more difficult to predict than temperature. And precipitation is also tricky, not just in quantity, but in distribution. So is it a little bit every day? Well, then we'll never have another fire season. Or is it periodic, where you have lots of rain for a couple of weeks and then, 6 weeks of dry? Well, then you have very different fire dynamics, for example. And so it's, I guess what we're trying to communicate is that we can't necessarily wait to change our forest management practices until we can predict the future, because there's just too many risks. So let's start changing our forest management practices to a more resilient approach so that we're ready no matter what the future brings.
Perfect. Thanks, Caren. Thanks, everyone, for the questions. I don't see any more questions being typed. I guess last call for questions on the conference call line. Again, hit *6 and that will unmute your line. If not, I'll just...
I should say that we didn't project an increase of wildfire for the study area because the work that's been done, the projections that have been done, don't show an increase in fire risk or fire hazard for this part of BC.
Okay, great.
We also didn't include fertilization that can occur due to carbon dioxide or the downside risk associated with local population adaptation, so provenances, and we just hope they cancel out, partly because there isn't a productivity model that incorporates all these different things that we can then feed into our landscape scale model. But I know people are working on that and developing that, so that might be part of the next phase that we build in.
Great. Okay, Trevor Murdoch has a question here. So now that the next stage of future climate projections are daily, do you intend to make use of those in the next stages of this work? It might allow you to address some of the uncertainty you were just referring to in terms of how precipitation changes play out.
So we are using daily future projections in our other study area, which is in the Greater Penticton Creek watershed, which is a much drier environment, and it's much more exciting in terms of wildfire and wildfire risk. And so all the fire indices are calculated based on daily weather, and so it's awesome that those climate projections are now available at the daily time step, because otherwise it's pretty difficult to get at wildfire unless you're just dealing with really long-term drought.
For sure. Okay, great. I guess this is we only have about 5 minutes left, so last call for any questions on the chat box or on the conference call line. If that's it, I guess we'll wrap things up. So again, thanks everybody for joining us today for the FACoP webinar. We hope you enjoyed it. And obviously a very big thank you to you, Caren, for your time and effort, for a great presentation. Any last comments from you before we sign off?
No, thanks, Annette, for organizing this. I really appreciate having that community practice online. It's great.
Great. Well, thanks very much. Thanks again, everybody, for joining. That's it for us today. So have a great week, and we'll catch you next time.